Morning, everyone. So yesterday we started looking more at the solubility chart. We saw sort of two styles of the question. One of it was writing what's referred to as a complete ionic net ionic equation. All double replacements always make it look like we create two new things, but we saw that especially if things were soluble, if things were actually aqueous, water has actually separated positive from a negative. Those are actually not physically bonded together, and we saw a few examples that they may be spectators. I'm going to give you a quick practice question of that style of problem, writing the ionic equation, and then towards the end we had a selective precipitation example. Basically, I may have a beaker that contains a whole bunch of different ions, and what our job is to use this precipitation method, find things that only precipitate one of the solid. I can filter off that solid, and I can separate the ions one by one. So let's just do this as a quick warm-up here. Question number one, like we did last day, I want you to write the formula equation, write the complete ionic equation, and write the net ionic equation for the following mixture. You will need to use your solubility chart for this, and I'm going to give you the problem. Lithium chloride. Let's react it with barium nitrate. I'm just going to get you to predict, balance, and classify. And then in question number 2 here, a little bit more challenging of a selective precipitation. I'll leave myself a little bit of room there. For selective precipitation, I want to take a beaker that potentially contains 4 different anions. This sign here is actually the negative ions. This beaker may contain some sulfide anion. It may contain some chloride. It may contain some carbonate and hydroxide. I definitely can't have a bottle that's just pure negative here, but I'm going to try to pull out salts one by one because these are negative ions here. You're going to try to find some ways, start putting in some cations, some positive ions that'll precipitate out one by one. There's many possible solutions, but you just want to list one. Again, I encourage you just to pause the video and you can come back and check your work afterwards. Starting off with the first one here, we have lithium chloride, barium nitrate. We expect it to be a double replacement reaction. So lithium is going to bond with nitrate, and then we're going to have barium with chloride. Right? We always have a solubility chart, so you can check all the compounds. Remember I said for a properly worded question, the reactants there should always be aqueous. The whole point was to dissolve them, get the ions broken up first so they can mix easier. In this case here, if you remember your little tricks here, lithium is an alkali ion. Lithium salts are always going to be aqueous. So aqueous, aqueous, I don't even need to bother checking those. Nitrate salts are also always soluble. Doesn't matter, so barium, those are aqueous. So really the only one I want to check here is actually barium with chloride. In this case here, let's check barium and chloride. So I'm down on this chloride row here. Well, no, barium's not silver, it's not lead, it's not copper 1. Barium would actually be up here. Barium with chloride is actually fully soluble. So there we go, we have aqueous. We only need to check the solubility chart here for a double replacement reaction. Going from this to the complete ionic equation, I take anything that I've listed as aqueous and I break up the ions. Even though my bottle may be labeled LiCl, this one here is actually completely separated. It's actually become Li plus, Cl minus. The barium nitrate is also aqueous, so Ba plus 2. Sure, I have 2 nitrates. Notice that the polyatomic sticks together. We're going to have lithium nitrate here, so I have Li plus and I have NO3 minus. And similarly, we have Ba plus 2 and we have 2 Cl minus. Everything was actually aqueous, right? Remember on the right-hand side, it could be 1 solid, it could be 2 solid. This is the first time we're seeing both of them aqueous. Well, what would that mean then? Well, our net ionic equation says if there's any spectators, if there's anyone that's the same on both sides, let's just cancel them. Uh-oh. Lithium is a spectator. 2 nitrates are a spectator. So I realized I didn't balance this one here. Because I needed 2 nitrates here, that should be a 2 in front, 2 in front. So with that balancing, right, everything cancels out. 2 lithium, 2 lithium, 2 nitrate, 2 nitrate. We have 1 barium, 2 chloride. Wait a second, everything is a spectator. So all that's happening here is my first bottle, which was labeled LiCl, was actually Li ions and Cl ions swimming around. My second bottle here, which was labeled BaNO3, also aqueous. It was just barium ions, nitrate ions. When I tossed them into one container all at once, now I just have all 4 ions. I potentially could have formed a precipitate, but everything is fine dissolving with each other. So in this case here, everything is a spectator. So we're going to actually cancel everything as spectators. Right? All the ions, none of them change. So therefore our conclusion is actually a no reaction. So that's another possibility out of the double placement reaction here. Even though it makes it look like we've created two new compounds, they just switched partners. In fact, this is just shorthand. Well, it's still aqueous. They're still separated. All that's happened is now all four ions are now in the same beaker, but they're perfectly fine dissolving with each other here. Right? So that's an interesting case here. Basically, there's no net reaction, even though the balanced formula equation looked like we created two new things. Right? For the second one here, again, we're going to make use of our trusty solubility chart here. This one's a little more challenging. The one we did from yesterday was we had a bunch of positive ions. That means I need to add negative ions. In this case here, we have a mixture that potentially has negative ions. I want to pull them out with a positive ion. The reason why it's more tricky is because negative ions, that's usually where I would start off to start doing my crisscross sort of combinations here. Again, it doesn't really matter which one you pull out first. Sometimes you have more options than one. I'm going to look at these ones here. I have sulfide, carbonate, hydroxide, chloride. I want something that's soluble with 3 of these, but low soluble with one of them. So let's just match up here again here. So we have sulfide, we have hydroxide, we have chloride, and we have a carbonate. So I want to add one thing. The first one is going to be the hardest because I need it to be soluble with 3 out of the 4, but just solidified low soluble with one of them. So what I'm noticing here is I'm noticing, well, look, strontium is good with sulfide. It's good soluble. Strontium is good with hydroxide. That's going to be soluble here. Strontium would also be a part of the all others. Strontium is fine with chloride. Strontium, however, would not be good with carbonate. Again, as we work down on our table here, we end up getting more and more solid. So in this case here, if I manage to add a strontium ion, the strontium carbonate combination will end up precipitating strontium carbonate as solid. Strontium would be fine with the other 3s. Again, I'm not going to have ever a pure bottle of just pure strontium, right? Charges are unstable. I need to have some counterbalancing ion. So let's add strontium nitrate. Well, where did that nitrate come from? I'm using the fact that nitrate salts are always going to be soluble. Basically, I don't care about the nitrate. This becomes strontium ion and 2 nitrate ions like this. This will just produce the strontium that I need. And when strontium is in the beaker here, it's perfectly fine dissolved with 3 out of the 4, but strontium is going to pull out the carbonate here. So add the strontium nitrate to precipitate out the first one to PPT strontium carbonate. So you add strontium, any solid that forms is going to be strontium carbonate. I'm going to imagine then filtering, then that solid is completely gone. Now second, I have a beaker here. Now it only contains sulfide, chloride, and potentially hydroxide. Now I don't need to worry about the carbonate. I should have more choices for the next one. Again, I've sort of marked off for us here. We have chloride, we have sulfide, we have hydroxide. What's something that's good dissolving with 2 of them, but not one of them, right? So we want to pull them out one by one here. Let's add, for example, magnesium. Magnesium is perfectly fine with sulfide, just like strontium was fine. Magnesium would also be fine with chloride, perfectly soluble, but magnesium is actually down here. Magnesium is not good with hydroxide. When the concentration of magnesium gets high enough, that's going to be low soluble, that's going to precipitate out. So second step here. Again, this is not the only way of doing it. Let's add magnesium, again, as a nitrate salt. This is going to generate the magnesium ions. The nitrates I don't care about. The nitrates are just going to be a spectator. This is going to end up precipitating out MgOH2, magnesium hydroxide. Good. Now that's gone. It's going to solidify out MgOH2. Again, the implication there is we're going to filter off all the solid. Now we have a container with just sulfide and just chloride inside. And now I have should be more and more choices because now it's just between these two things here. I need something that's not good, low soluble with sulfide, but soluble with the chloride. So let's add in here any random compound. Let's take tin. Right. So tin is +2. Tin is not any of those one at the top. Tin is going to solidify out low soluble with sulfide, but tin is on this top here. Tin is perfectly happy being dissolved in with chloride. So let's add in a tin. Did it have to be tin? No. But tin is one example. You're never going to have a bottle of just pure tin positive, right? Charges are unstable. Let's have the counterbalancing nitrate here. This is going to guarantee I'm going to have the tin ion released, and that's going to precipitate PPT SN with the sulfide, SNS. And then lastly, again, if that ends up happening here, I end up solidifying out chunks and chunks of this tin 2 sulfide. Now I just have chloride. Now I just need something that will precipitate just chloride. I don't need to worry about anything else. And in step number 4, well, let's put in, I don't know, silver. So let's add in, as a last step, upon filtering in between all these steps here, let's add in silver nitrate. That's going to give you silver plus and nitrate, and this is going to give you the silver ions to precipitate out AgCl. Again, what I want to emphasize here is this is not the only solution. You could have found another combination that also works, but your goal is to add in compounds one by one so that you can pull out solutions you can pull out the ions one by one. Today we're just going to start introducing a little bit more of the math again. These saturated solutions, we've been saying they're at equilibrium. The dissolving rate is equal to the recrystallizing rate here. Being in equilibrium, we can do KEQ again. It's just going to be given a slightly different name in this section here. We're going to actually call this KSP. Right? So KSP, this is going to be an equilibrium constant. As we introduce this here, we'll work through a problem or two. So I want you to just consider with me here. Consider a saturated MgOH2 solution. Okay? The implication here, we're saturated, right? So saturated already means equilibrium. So what's the forward rate? What's the reverse rate? In this case here, the dissolving rate is equal to the recrystallized rate. So that part there is true. It's in equilibrium. What's actually happened for you to make the saturated solution here is you've actually hit the solubility. Solubility is describing for you the max amount that can dissolve. Right? Sort of is this limit, you basically packed out the solution here, it can't handle dissolving anymore. So because you've put in the maximum amount here, if I look outwardly here, I need to have some undissolved material present. I still have to have undissolved material because I still need to have a dissolving rate. That's the forward reaction. The magnesium ions, hydroxide ions are going to jump into solution. Just as the ions are enough now, they're going to collide with good energy, good geometry, and they're going to solidify back out to reform the crystal. That's the recrystallization rate. Remember, I need to have both reactants and products present for you to be at equilibrium. In this situation here, although there were two ways of forming the saturated solution, we'll rehash that a little bit. We're going to always put the solid on the left side. So the solid in this case here, the only precipitate I'm forming here is magnesium hydroxide. This one here is a solid. The dissolving, I'm going to say, is our forward reaction. That's going to dissociate to become magnesium ions and 2 hydroxide ions. Because we've said saturation, because we're at equilibrium, there is a recrystallizing rate here. That's the reverse reaction here. That takes these aqueous ions and recrystallizes them back out to form MgOH2. Again, macroscopic properties are constant in time. So it looks like nothing's happened. It looks like we've hit this balance. It looks like everything is stopped. And yet we see, again, in chemistry, time and time again, the reactions are continuing to occur. So microscopic reactions continue. RxN is just reactions. Okay. How can these both be true? How can it look like nothing is changing, and yet the reactants are constantly becoming products are constantly becoming reactants? Well, it can happen if the rates themselves are equal. Because this is an equilibrium system, what I want to do is I want to do a KEQ. KEQ here is your equilibrium constant. If you remember from our last chapter here, this one here is the concentration of products divided by concentration of reactants. For this whole chapter here, because we're always going to be dealing with a precipitate, one of them is a solid, you have to remember for KEQ, we always ignored solids. Solids have a constant composition. Solids are just a fixed number. They don't shift to equilibrium. The advantage of putting the solid on the left side as the reactants, basically my KEQ in this situation will be the concentration of magnesium ions multiplied by the concentration of hydroxide ions. The numbers, remember, go up to the power there. Every now and then they try to squeak in, oh, that 2 there, oh, inside the bracket here. In general, that's wrong. The numbers should never go in the square bracket. In this case here, we see because the numbers go up into the powers. Well, the reactants would have been the concentration of magnesium hydroxide, but again, we ignore the solid, so that's actually going to be divided by 1. We're going to give this, again, a special name in this section here. I'm going to rename this here. The constant is actually just K, fine. But in this chapter here, because it is going to be, solubility tells you it's going to dissociate, it's going to break it to form ions, and it's a product of your soluble ions. We're going to call this KSP. The SP actually refers to a solubility product. So while in general you can call this, yes, it's an equilibrium constant, maybe they now call it a solubility product constant. At the end of the day, it is KEQ. All right? So what is the KSP given by? The KSP is given by Mg plus 2, multiply it by the OH minus, that 2 and the balance coefficients end up going up to the powers. I remember when I was first studying this, I was super confused. I was like, what is this KSP here? Really think about it. It is KEQ. So what things do we know about KEQ? We know KEQ here, there's no units. Same thing here. KSP here has no units. We know only temperature changes this KEQ. Can change KEQ. In this case here, we're just going to give it a different name. Only temperature can change KSP. Things may dissolve better or worse depending on whether it's hotter or colder. Right? At the end of the day, however, it is an equilibrium constant. What if your KSP is much bigger than 1? Right? Again, we think about this KSP as this product over reactant ratio. If I have this fraction here as bigger than 1, it's a large number, that means I have to have lots of numerator, not a lot of denominator. So in this question here, KSP greater than 1. In chapter 2, we already said more products, or products are favored. And in this case here, because we're always putting solids on the left side, I know my products are just going to be the ions. Having more products means you have more ions. So more ions, going to be more conductive, all that's true. The only reason why I would have more ions is because this salt here is actually more soluble. It's not that hard to break this up here. Every time it breaks up, it creates more and more and more ions. The higher the ion concentrations, the bigger this KSP, KEQ number is going to be as well. More ions, so therefore the conclusion is we actually have a higher solubility. It's more soluble as a salt. Again, KSP here is tracking concentrations. KSP can't go into the negatives. If KSP is actually less than 1, bounded by 0 there. If it's less than 1, if this fraction, products over reactants, is supposed to be some ratio that's less than 1, for it to be a tiny number, I need to have low number of products, high number of reactants. Now, in this case here, it's a little bit strange. Remember, for us, the reactant here is actually a solid. I don't really talk about the high concentration of solid. I can't change that number, but definitely speaking here, we need to have low product concentration. The products are our ions. We can say in this situation, reactants are favored. So I have more reactants at equilibrium, which means here I have very few ions, and few ions means I have a less soluble salt. Right? But aside from that, everything else is identical. Everything else is KEQ, changed by temperature, all that's true. Okay? On our first lesson, I already alluded to there's 2 different ways of forming a saturated solution. It's important you identify which way that we're doing. Right? So let me just rehash this. There are actually 2 ways of making this saturated solution, right? This mixture where we have the solid in equilibrium with the ions. I'd say the easier of the 2 ways is to start off with the solid. So first way, let's just dissolve the solid. Okay. So I wanted to eventually make a beaker that's saturated. I want to eventually have MgOH2. That's my example right now. So I want to have MgOH2 as a solid. I want it to broken up to form magnesium ions, hydroxide ions. Well, let's pretend to make that. Just take some magnesium hydroxide. It's totally okay as a solid out here, and slowly just drop it in there. Right? So as I dissolve the solid here, what's going to happen here is I started off with just MgOH2. That's good. My solid is already on the left-hand side. By dissolving the solid, the first smidgen that I toss in is going to break up. Fine. I'm going to get magnesium ions, I'm going to get hydroxide ions in a 1:2 ratio. I drop in a little bit more, it breaks up. Drop in a little bit more, it breaks up. But magnesium hydroxide is fairly low soluble. It doesn't take that much. I've dropped in enough that, it's now precipitated out. Now I can't dissolve anymore. As it can't dissolve anymore, I wait a little while here for an equilibrium to be established. The magnesium ion, hydroxide ions are going to constantly be dissolving, but those ions are constantly going to be colliding, good energy, good geometry, and they're actually going to start crystallizing out. That's actually going to give you the reverse reaction there. All right? So when you dissolve the solid, because, in this case here, because the ions dissolve from the solid, they will follow the mole ratio. They're going to obey the mole ratio. We're going to do a problem with this in a second here. If I have an X of magnesium hydroxide I can dissolve before I hit the saturation limit here, in following the mole ratio, it's a 1:1 ratio with magnesium, 1:2 ratio. I'm going to get X of magnesium and 2X of hydroxide. Now, truth be told, for any powder that actually ends up dissolving, that powder is actually gone. But remember, for saturation means we are in equilibrium. So saturated means we're in equilibrium. Even at equilibrium, even sort of subtracting off how much is actually broken off, I still have to have undissolved material present. Okay, so that's the easier way of doing the problem here. I'm going to give you a quick practice question. I want you to calculate, similar to questions from earlier, calculate the molar solubility of Ag2CrO4, and I'm going to give you, okay, there's actually a table for this later on. I'm going to give in the KSP for this salt is 1.1 times 10 to the negative 12. Right? I'll show you a KSP table later on. Okay. First things first. So KSP is an equilibrium constant. This is the number, it's quoted at 25 degrees. First, you'll notice that this is a 10 to the negative 12 number. In fact, all the KSPs that we have are going to be really, really tiny numbers. Because the fraction is really, really small, we know reactants are favored. Right? That's what we had concluded earlier. Reactants are always going to be the solid side. So in this case here, it means we don't have many ions. The lower this number, the less soluble salt is going to be. Right? Again, we're going to assume the easier case is when the ions follow the mole ratio. So I'm going to start off with, in this case here, Ag2CrO4. It was just solid here. You start tossing it in. It doesn't take much of it, and it's already solidified out. We're going to put the solid on the left side. Usually in these questions here, I always write these two equations. The dissolving reaction, the equilibrium. This one here dissolves to form silver ions and dissolves to form chromate ions. And because this is an equilibrium expression, right, so this is solid, these two other ones here are aqueous, I'm going to also write out the KSP expression. It's like writing out the KEQ expression. It's basically going to be products over reactants. Well, the reactants are always going to be solid, so don't worry about them. It's just going to be the product of the soluble ions, silver squared times chromate. Right? All right, so what's the question asking? It's asking us for the solubility of the silver chromate. As I try to dissolve the salt in, how much until you've actually saturated the solution? I'm just going to give you a hint here. Solubility is a number that always describes the solid, right? It describes how much dissolves. Although solubility is related to this KSP, they are numerically different. KSP is more so after this breaks off, we end up forming the ions. As you multiply the ions this way, KSP is the number that ends up as the product. Okay, so KSP, although these two things are related, in general, let's actually write it down right now. So in general, if I have a bigger KSP, let's just work through the math here. If I have a bigger KSP, that means I have big ions, so lots of silver, lots of chromate. Well, where did the chromate and where did the silver come from here? Well, they had to come from the solid. If the solid is managing to break off to form a lot of ions, it actually refers to more soluble. It would actually mean a more soluble salt. In general, bigger KSP means higher solubility or bigger solubility. But I want to emphasize with this example, even though there's this sort of correlation, when one gets big, the other gets big here, KSP and solubility numerically are still different values. Solubility is expressed in moles per liter, where KSP here actually has no units. Okay, so we did the easier of the two ways of making a saturated solution. Let's just start off with the solid. Let's keep tossing it in until the precipitate is formed. So it's just left over there. I don't know how much I tossed in. Let's put in an X. Because I started off with the solid, the ion concentrations that break off from this X here, they have to follow the mole ratio. So if I manage to dissolve X moles per liter, I'm going to get 2X of silver, and I'm going to get X of chromate. That's the dissociation reaction. As a general rule, if you have these two numbers, if I have placeholders, X's, whatever, if I have these ion concentrations, you can sub them directly into the KSP expression. Because we know these are the amounts already at equilibrium. These are the amounts already when we're saturated. It's like having an ice table, already having that E row, and basically putting the numbers directly in. Now, this is not super nice. So we have KSP, great, I have this number, we said it's tiny, 1.1 times 10 to the negative 12. Our silver is actually going to be 2x. Do I still need to square it? Definitely. Okay. We treat these as two totally separate equations. We did the two because we had to follow the mole ratio. So the silver was already doubled. But as I re-express that statement here into KQ constant here, I also need to square it. So effectively, it's been doubled and squared. The chromate here is just going to be an X. Let's clean this up a little bit here. When I have a bracket like this all squared, it's like 2x times 2x. It's 2 squared x squared. So getting here 6.5 times 10 to the negative 5. All right? So I went through this math here. I took the KSP here as given in the problem. This was your equilibrium constant. This was telling you reactants are favored, and now you managed to find X. Go back and reread the question. They wanted to know the molar solubility. The solubility describes for us what's the maximum dissolved solute before it hits equilibrium. And you notice I actually put an X for that. Perfect. X is actually the solubility. X followed the mole ratio, so the units here are actually molar. This one here is actually the molar solubility. Again, two ways to interpret this. I was dissolving the solid, so you can say here, you can dissolve as a maximum. You can dissolve 6.5 times 10 to the negative 5 moles per 1 liter of solution. Or, because it's molar, where we think of it as moles per liter, we think of it as concentration, you can then say the concentration of this solid, let's say concentration of the solid in the solution is 6.5 times 10 to the negative 5. And no real surprise there because, hey, I dissolved 6.5 per liter, so therefore the concentration in that liter is 6.5 times 10 to the negative 5. Right? That is the easier way of asking the question here. I can follow this question up. Now that you know what that number is, let's say part B of this question here, I want you to find for me what mass of silver chromate can be dissolved into 500 milliliters to form a saturated solution. Right. So we already found the number here. You can manage to dissolve 6.5 times 10 to the negative 5 for a given liter. They now give you a volume, and they're also asking for mass. Anytime they ask for mass here, my hint is you're just going to need to use molar mass. So let's see if we can just finish this up here. How many grams of silver chromate would I need? Starting off with the volume, because our concentration here is expressed per liter, I'm going to convert that to liters. Keep track of your sig figs. 500 with a decimal is 3 sig figs. So 0.500 liters. That's the solution I want to make. The concentration I just found, you can dissolve enough to have 6.5 times 10 to the negative 5 moles for a given liter. And given the molar mass of silver chromate, I can then calculate over to grams. Okay. So taking out your periodic table again here, we have silver, which is 107.9, and you times 2 because there's 2 of them, plus chromium, which is 52, plus 4 times 16. The molar mass here is 331.8, and then you just multiply the numbers through, 0.5 times 6.5 e negative 5. I'm going to be off by a little bit of rounding here, but in this case, you can dissolve 0.0, 2 sig figs is the limit here, so it's 0.011 grams per 500 milliliters. So even though this is a molar solubility, even though that was expressed per liter, if my total volume is actually not quite a liter, I just multiply the C times V and I end up getting the moles. Okay, that's one way of doing it here. In this question here, I actually gave you the KSP in the problem. I'll show you the KSP table later on. But basically, if I can't find it in the question, you just look up the table. Oh, it's this salt here. What's the KSP that they gave you for it? That's the first way of making a solution. Let's end off with the second way of doing it here. The first way was nice. You dissolve a solid, everything follows a mole ratio. The second way here, we already alluded to in a previous lesson, we're going to mix two solutions together. Right. So back to our MgOH2 example here. Let's pretend we have some solution here that contains magnesium. We have another solution here that contains a hydroxide. We did this a little bit on the very first lesson here. But basically, you just toss these in together. They're going to end up finding this third container. They realize they don't dissolve very well. They will eventually also solidify out to become an MgOH2. What I want to show you in this situation, not only is there going to be a dilution, so solutions get diluted when mixed. So there's an added C1, V1, C2, V2 work that we need to do. But sort of more importantly here, you see that magnesium comes from its own solution. Hydroxide comes from its own solution. Even if I write out the equilibrium expression here, there's no reason for magnesium to follow the mole ratio. Magnesium could have been 3 molar to begin with. I just randomly tossed it in with 1 molar hydroxide, so be it. Right? They were totally different solutions. They don't need to obey the mole ratio. So what I want to show you in this case here is we throw in the magnesium ions. Usually magnesium will be complex with some salt. The hydroxide also having some counterbalancing positive. I don't really care about them. They're spectators. Basically, the magnesium and the hydroxide, upon being diluted, they get mixed in the same solution together. When the concentration of the magnesium and hydroxide get high enough, they're going to end up solidifying out, also forming this precipitate here. Realistically, what's happening, let me just give you an example. Maybe I'm tossing in magnesium nitrate, and I'm tossing in, I think, sodium hydroxide. That's what we did from earlier. Well, where did the nitrate and where did the sodium come from? I'm just guaranteeing that these ones here are going to be soluble. This one here ends up forming a salt. If you did your net ionic stuff here, MgOH2, that's known to be a solid, but then the NaNO3, that one there is definitely going to be aqueous. Obviously, you need to balance it as well, right? Even though in this situation, magnesium came from its own solution, so let's write down here, Mg2 plus comes from, let's say, solution 1. The OH minus comes from solution 2. That's why they don't really care the mole ratio. The MgOH2, which is our precipitate, which is actually the product in this equation, before you write KSP, I'm not going to write KSP for this expression because this is not the equilibrium. When you identify what the salt is, you're still going to put the solid on the left side. It was actually a product of your reaction, but I have MgOH2 here, and this one ends up forming, let's say, Mg2 plus and 2 hydroxide, right? I'm going to still have the solid on the left side so that when I write out my KSP expression, products over reactants, KSP is still going to be, just like we did earlier, magnesium times the hydroxide squared. But in this case, I want to just imply to you the magnesium will be some number, the hydroxide will be some number. They will be regardless of this 2 here. They came from 2 totally different solutions. Sure, I need to do a dilution and a mixing question here, but they're not necessarily going to follow mole ratios. But if I have these 2 numbers here, you can totally fine drop them into the solution, drop them into KSP. Okay. So let me just do one of these examples for you here, and we'll end off with this. So new example, I may be at totally different temperature. Maybe I should write this down here. Ions come from 2 different solutions, so they do not follow the mole ratio. So one way follows the mole ratio, one way doesn't. You just need to identify for yourself which way is which. So let's do this example here. A saturated MgOH2 solution is made by mixing, so that's our second way, mixing 20 milliliters of 0.15 molar MgNO3 with 50 milliliters of 0.110 molar NaOH. Okay, I want you to find for me, calculate the KSP. Calculate the numerical value. What is the equilibrium constant at this particular temperature? Right? If you like, you can start off with the picture. So we have here, starting off, we have 20 milliliters. The concentration starting off is 0.150 molar. This is currently MgNO3. I'm going to mix this solution together with another solution here. The other solution is 15 milliliter solution, a little bit more volume, a little bit lower concentration, 0.110 molar, that's NaOH. I mix these 2 together. Easy problem first. I mix 20 and 50. My total volume is going to be 70. There is a dilution aspect that I need to do right from the start. Regardless of this saturation and solubility stuff here, there's a C1V1 C2 V2 I need to do for magnesium nitrate. There's a C1V1 C2 V2 I need to do for the sodium hydroxide. So let's do that part first. 0.150, volume is 20. What's the new C2 if my final volume is actually 70? On the other side here, we have concentration 0.110, volume is 50.0. What's the new C2 given my final volume again is 70? So let's just do the dilution. This is one added feature. If you do a mixing question, you have to do a dilution. The new concentration of MgNO3 has actually dropped quite a bit, and now it's only 0.0429. molar. On the other side here, 0.110 times 50 divided by 70, the concentration of the NaOH is equal to 0.0786. Okay, so do a mental check for yourself. It makes sense that these numbers here are now a little bit tinier because the pool has gotten bigger. Now, I don't really care about the nitrate. I said that's a spectator. What I'm thinking in the background here is, if you take magnesium nitrate, nitrates are always soluble, just one-way arrow. This ends up forming magnesium and 2 nitrates. If you have 0.0429, because this one here is starting from the salt, this will follow mole ratio. It's 1 to 1. I'm going to get 0.0429 molar. That's the part that I care about for magnesium. I actually do end up getting 0.0429 times 2. I get 0.0858 of the nitrate as well, but that's a spectator. I don't really care about it. How about the other side here? We have sodium hydroxide. The NaOH is a 1-to-1 ratio, Na plus hydroxide. If I have 0.0786 of my compound, this one here is going to be 0.0786 of sodium. Again, I don't care about that one, but 0.0786 molar of the hydroxide, that's the part that I care about. Keep it in the back of your mind here, what is potentially the precipitate that forms? In this case here, we were trying to form a precipitate of MgOH2. Saturated means we're at equilibrium. So right away, if I know what potentially is the precipitate that forms, although in the ionic stuff here, we could form 2 precipitates. For these math questions, there will always only be 1. Once you know what the precipitate is, I want you to write solid on the left side, MgOH2, dissolves to form Mg plus 2, and I have 2 hydroxide. And also write the KSP expression. Basically, the 2 ions concentrations multiplied, the coefficient goes up into the power. These are 2 totally separate equations, even though what's going to actually happen is magnesium as a reactant, hydroxide as a reactant, it's these 2 that actually combine together to form the MgOH2. At first, you may be like, oh, MgOH2 is actually a product. I'm still going to put the solid on the left side so that my KSP works out nicer. So, in this question here, we're mixing solutions. We're not expecting these 2 numbers here to follow the mole ratio. You look at the numbers, they definitely don't. The magnesium is 0.0429. That came from your first solution. Be really careful here. The hydroxide I found was 0.0786. Well, what about this too? Well, what about it? I told you it didn't follow the mole ratio. They actually told you the concentration of hydroxide is 0.0786, so that is actually exactly 0.0786. And you look at these numbers here, they don't quite follow the 1 to 2 ratio. 1 to 2 ratio would be like 0.084 or something. This is slightly less than it, but I could care less about this 2 here. But these are the amounts that I managed to dissolve to hit a saturated solution. Whenever you have these 2 amounts here, you put them in here. As you plug them into the KSP expression, the magnesium is going to be 0.0429. The hydroxide I calculated was 0.0786. It didn't follow the mole ratio. Do I still need to square it? Yes, I do. Right? Because based on the KSP, based on this equilibrium expression here, that 2 does go up to the power. Even though this hydroxide number was not quite double, it didn't quite follow the mole ratio, that 2 does go up to the power, and therefore calculates the KSP for you. 0.0429 times 0.0786 squared. This gives you 2.65 times 10 to the negative 4. Because this one here is a KEQ, it should have no units. It's a fairly small number, even though relatively speaking it's actually larger than some of the other ones, 10 to the negative 9, 10 to the negative 10. But basically, we know not a lot of salt is going to dissolve. The bigger this number is, the more salt is going to dissolve. Okay? So practice a few questions through your worksheet. If you have any problems, just let me know. Thanks, guys.